Good morning, everyone. So we're going to pick back up with one last slide here from section 4.3 before we head into the second half of chapter 4 and talk about something called redox reactions coming up next. But to kind of finish off our topic on acid-base reactions, we have a couple of reactions shown here where we're forming CO2 gas. And one of the things that can happen when you form a gas in a reaction is it just, of course, would fly away or float off the reaction. So we can see that forming a solid allows the reaction to take place. When we have a metathesis reaction, we have to form a solid to drive the reaction to take place. Otherwise, we're just dissolving ions in each other. We also saw then you could have kind of a metathesis reaction, though without precipitation, where you have an acid and a base reacting together, where you can make a salt and water. And water is what we saw was kind of driving that reaction to take place because water was something that could form that didn't go back into its ions. And we can also have CO2 gas or like a gas in general form that floats away from the reaction mixture. So here in this acid-base reaction, we have H plus and Cl minus from HCl reacting with a carbonate ion. Now calcium carbonate's insoluble in water, so this thing starts off as solid here, not AQ. And then it dissolves in the acid as the carbonate ion reacts with the acid to form H2CO3, which is actually unstable in water and decomposes into CO2 in water. So anytime we make H2CO3 in water, it would just decompose the CO2 into water. And so we get CO2 in water from what would have been carbonic acid forming, and then calcium chloride as that byproduct for the calcium ion and the chloride ion left over. One of the things we could do is we can always write a net ionic equation. Sometimes we do this, or sometimes it seems like we do this just to make you write a reaction, but it also allows us to see what the net change is. So if we start thinking about how we would write the net ionic, we have to keep the solid as a solid. We can't dissociate it because it's not water soluble. And then the HCl is a strong acid. So you're just trying to ask the question, is this a strong electrolyte in water? Has to dissolve to be any kind of electrolyte, doesn't dissolve, so it's not a strong electrolyte. HCl is a strong acid, and so that is a strong electrolyte. So that would be 2 H plus ions, 2 chloride ions in the solution. I could write AQ for each of those. Calcium chloride is a water-soluble ionic compound, so that would be calcium 2 plus 2 chloride ions, both of those AQ. And then CO2 and water, those are just molecular compounds. They're not acids or bases. They're not strong acids or strong bases either. So they're just CO2 gas and water liquid. CO2 is the gas that floats away. Water also forms and helps drive this reaction to take place. And so we can only cancel out one ion here, so the only spectator would be the chloride ion. So for a net ionic, we could cancel out the chloride and just write calcium carbonate plus 2 H plus ions. Aqueous forms calcium 2 plus CO2 plus water. And this helps us see that there is a net change that takes place during the course of the reaction. So that's really what you see from trying to write the full ionic to the net ionic, is just trying to see what is the actual net change that happens in a reaction. So we use things like sodium hydrogen carbonate in the form of like baking soda, like when we cook, because it can help release CO2 gas. It can help bread rise, for example. And so it works by taking HCO3 minus, absorbing 1 H plus, and you make H2CO3 again, which then decomposes into CO2 and water for the same reason as the first reaction. So we can have things like sodium hydrogen carbonate react with acid to form a salt plus CO2 plus water. So we're seeing the same type of reaction as above. If we want to write this net ionic, we'd have sodium plus, and then HCO3 minus is the ion in the ionic compound sodium hydrogen carbonate. So this is an entire ion in and of itself with a minus charge. You might recall carbonate, from the previous examples, a 2 minus. If it absorbed an H plus ion somehow and made the hydrogen carbonate ion, that's why this charge is now -1 instead of -2. If we go all the way to H2CO3, that would be carbonic acid. Just thinking about nomenclature here, this is named for being an acid, and then once that forms, you get CO2 and water in its place instead of H2CO3. HBr is a strong acid, so it's a strong electrolyte in water. And I could write AQ tags for all the ions. I'm going to neglect writing all the AQs in, but I'm going to get sodium plus plus Br minus on the product side, and then plus CO2, and then plus water. I'll throw their tags: CO2 gas, water liquid. And so then the only spectator ion here would appear to be bromide. Actually, I get two spectators. Bromide and sodium are in identical forms on both sides of this chemical reaction. So my net ionic equation would look like hydrogen carbonate ion plus H plus goes to CO2 plus water. And that's a net ionic equation that's used a lot in cooking applications. We use baking soda a lot in applications of cleaning, where we're also just making CO2 and water. So another reaction is shown: sodium sulfide plus sulfuric acid forms sodium sulfate plus H2S. So H2S here is also a gas. I don't know if you'd predict it to be a gas, but if you know what it is, you probably would, because it's the smell of rotten eggs. It's that gaseous odor you get on like the smelly smell from like an egg, for example. And so this is just an acid-base reaction that's taking place between sodium sulfide. So we have two sodium cations, a sulfide ion. H2SO4 is kind of weird because if you recall, only the first H is strong. I might write this as H plus HSO4 minus, because this here is not a strong acid, that's just a weak acid. And so then this would yield two sodium cations plus SO4 2 minus on the product side, and then H2S being a compound that's certainly not a strong electrolyte. It's not going to dissolve in water. It's flying away from the solution and leaving the solution as soon as it forms. And so our only spectator here would be the sodium ion. And so what's going on here is the H plus ions are being taken away from the sulfate ion to form H2S, and then we're leaving behind the sulfate ion. So we'd have S2 minus plus H plus hydrogen sulfate ion yields sulfate ion plus H2S. So just a few examples of some reactions that we can write, some net ionic equations that kind of go along with those reactions and see the net change. So forming solids can help drive these types of reactions to take place. Forming water can help drive these reactions to take place. Or forming a gas. You form a gas that flies away from the reaction mixture. It doesn't allow you to go back to the reactant. So these are things that allow you to take a reaction to 100% yield. That we're not going to get one of those equilibrium type reactions. If you think of like a weak acid partially dissociating, if you're ever wondering, does a reaction partially take place? Well, if you have something that as soon as it bumps into another cation solidifies, then it solidifies and that reaction very quickly goes towards products 100% of the time. Same thing with forming a gas that flies away. It never comes back into the reaction mixture and re-reacts back to reactant, so that very quickly goes 100% towards products. Okay, so let's get into the next section of 4.4, which is on the topic of redox reactions. We'll see an example of that in a minute. In fact, maybe we can start off with a real basic idea of a reaction that fits the category of involving a change in charge. If we think of that reaction where we were making water from H2 and O2, what we're going to see here is that when we have elements, they're not going to have any charge on their atoms. They're going to be uncharged as they begin. We can probably imagine H2, neither atom of hydrogen has a charge associated with it. And then when we make water, we're going to see that hydrogen has a positive charge, oxygen ends up with a negative charge on it, and that the oxygen atom is gaining charge during this chemical reaction, and then the hydrogen atom is losing charge. And then the loss of charge is oxidation, so losing electrons during a reaction is oxidation. So losing electrons is oxidation. Gaining electrons is reduction. So we have oxidation and reduction that can take place. And so trying to figure out how we can account for charge, how can you know the rules for what the different charges of atoms are in compounds or in their elemental forms. And so we like to have some kind of a rule or some sort of a way to know how to understand what the charges are for different types of atoms and the different types of molecules and compounds that they're going to exist in. And so whenever we have some rules here, some atomic ions, this is very easy. If we know we have an ion, then the charge is just whatever the ionic charge is. So for example, if you have an aluminum 3 plus cation, the oxidation number is +3. If you have an oxygen -2 ion, the oxidation number is -2. So for atomic ions, charge and oxidation number just go hand in hand with each other. They're the same idea. So the charge is the oxidation number for the case where we have atomic ions. Now, a lot of times we don't have atomic ions. We'll have molecular compounds or molecular ions where we have to work out the charge of the atoms or the oxidation number of the atoms. And one of the things we're going to see is that the concept of charge versus oxidation number is not always exactly the same. For example, in water, we see, and we already wrote this before, that oxygen's a -2, hydrogen's a +1, but this isn't an ionic compound. This doesn't mean we're trying to say water's an H plus cation, an O2 minus cation, or O2 minus anion, and another H plus cation. Like, this is not what water looks like. Water really looks like where we have shared electron pairs, but what we're going to see is that we're going to end up with more of a positive charge. We're going to see we call a partial charge in chapter 8, we're going to call that a partial positive, and we're going to see the other hydrogen has the same charge, also positive, and that oxygen ends up with this partial negative on it, and that those charges aren't going to be quite -2 for O, +1 for H, but at least we can get the prediction from oxidation numbers that oxygen should be the more negative atom and hydrogen should be the more positive atom. So oxidation numbers we're going to see is kind of like a bookkeeping system for where positive charge is building up versus where negative charge is building up, or if we're building up more negative charge or more positive charge when we're comparing different types of ions. So a rule for oxygen in compounds is that its oxidation number is usually going to be -2. If we have a peroxide ion, we know that it's going to have to be -1 because a peroxide ion is the O2 -2 ion. So each oxygen has to have a net charge or oxidation number of -1. And so we have -1 in the case of peroxides. If we have the superoxide ion that's O2 overall with a -1 charge, then each O has to have a -1/2 oxidation number. So for example, and there's a bunch of examples on the next slide, if you have a compound like KO2, KO2 has to be potassium with a plus. That's the only possible charge for potassium. So potassium's charge and oxidation number would be +1. And then the two oxygens together have to be -1. And so then -1 shared across two atoms means the oxidation number per atom is -1/2. So oxygen's oxidation number in KO2 would be -1/2. So you can have fractional oxidation numbers. That's fine. There's nothing wrong with having a fraction for an oxidation number. And then oxygen also has to adjust its charge in compounds with fluorine, because fluorine, we'll see also in chapter 8, that it's the most electronegative atom, meaning it's the element on the periodic table that forms bonds with other elements that once charge the most. So if we have a compound like OF2, that if we're looking at this trying to see or trying to think where's the charge lie, and if we even get into a Lewis structure, the Lewis structure looks something kind of like this. Now, we don't expect you to sketch Lewis structures. We'll learn rules for this later. But we'll have a Lewis structure. It kind of almost looks like water in a way, just where the hydrogens are fluorines instead of H's. But what's going to happen here is fluorine's going to try to pull electrons in the bond towards itself to pick up a partial negative charge where oxygen goes positive. And the reason why oxygen goes positive, fluorines go negative, is just a consequence of the electronegativity of fluorine, which is a consequence of its position on the periodic table. It's a consequence of its nuclear charge, its size, some trends we'll talk about when we get to chapter 7. So fluorine just has the greatest desire for electrons, so it's going to be negative, and it's never going to want to go positive in compounds with other elements. It's going to make the other elements go positive so it can go negative. And so the rule for fluorine will be that fluorine's -1 in all compounds. So if you know fluorine's -1 in all compounds, then you know there's a -2 from the two F's. So the oxygen charge has to be +2. So it's like there's a priority system, if you will. The priority system would go fluorine is always -1, other elements adjusting their oxidation number accordingly. Oxygen usually -2 with a couple of exceptions like peroxides, superoxides. If it forms a compound with F would be another exception. And then the other halogens are usually -1 like fluorine is, except when they form compounds with fluorine, of course, or with oxygen, they would adjust accordingly. So we could have a compound like ClF, for example. So if we had a compound ClF, F's going to go -1, chlorine's going to go +1 to adjust its charge accordingly. So in compounds, fluorine's negative, ClF's a compound, so that would be -1 for fluorine, and then chlorine has to adjust its charge to positive to adjust accordingly. We'll see, again, some more examples on the next slide. Hydrogen. Hydrogen's usually +1 in molecular compounds, or probably better said, it's +1 always actually in molecular compounds, and it's going to be -1 in ionic compounds. So let's look at an example of hydrogen. Really easy example of a molecular compound would be water that we just did. So hydrogen +1 because this is a MC. Oxygen, it's normal -2, so that makes sense. +1 times 2 for 2, -2 for 0. If we sum up all the oxidation numbers per atom, we got to equal the charge on the overall molecule. So the same math for working out formulas of ionic compounds kind of applies to formulas with their oxidation numbers. So that's, you'll see a lot of math where just +1 times 2 is +2, -2 is 0. Another compound of hydrogen, though, in an ionic compound would be something like CaH2. We might recognize this from nomenclature because we know calcium's only a +2. We know this is an IC, right? Because it's metal, nonmetal. So calcium has to be +2. That's its oxidation number, that's its charge. And then hydrogen has to adjust accordingly to -1. So calcium 2+, 2 -1 ions for -2 to give us an overall neutral compound. And so we know this hopefully from nomenclature, calcium hydride. So hydride being H-. So we're just seeing hydrogen forms an H- ion with metals. It forms the ordinary +1 oxidation number in molecular compounds. And then hopefully any other atom we're asked about in a molecule, we can figure out by deduction from the other elements by their rules. So for example, if we have like K2CO3, and we're asked to figure out the oxidation numbers of all these atoms, the way we would kind of start is we know potassium, by its position on the periodic table, by its charge, has to be a +1 charge, +1 oxidation number. We know carbonate's a -2, but we can double check from the formula. We got a +2 here, so the entire collection of CO3 has to be a -2. Then if we want to check or go to oxygen, we know oxygen should be a -2. It has, there's some exceptions for O. We can make sure this isn't one of the exceptions. The exceptions for oxygen would be peroxides or superoxides. You would know that because peroxides and superoxides are only forming between O and certain alkali metals, and maybe rarely alkaline metals. You don't see peroxides and superoxides forming with other elements like carbon. You don't see peroxides or superoxides forming with other metals other than the group 1, group 2. So we don't have to worry too much about peroxides and superoxides unless we know the charge of the metal. It'll be pretty obvious when we have something like, say, CaO2. Like, this is a peroxide because you have a +2 and the O2 has to be a -2. So that's calcium peroxide. Each O would be -1 by oxidation number. If you saw something like, we did this example, I think, with nomenclature. If you saw like TiO2, that's just ordinary titanium oxide. So if you see this one here, we don't know the charge of titanium. We would have to know oxygen's a simple -2 oxide, 2 of them -4, to get titanium 4 oxide. So just making sure we see the nuance with O might seem complicated, but it's not, because we're only getting the peroxides and superoxides with the lithium group and some of the beryllium group. And they're pretty rare compounds. So that hopefully helps us see that oxygen has to be a -2 in mostly every compound, and we'll should be able to pick out the few types of compounds that there are some exceptions of with O. And so for oxygen, I have a total of -6. And so if I'm thinking for carbonate ion, what does the charge of carbon have to be? Like, this is the atom here that I can deduce, like from the rules of potassium and oxygen, so we can deduce that the charge or the oxidation number on carbon would be plus 4. So how do I know it's plus 4? Well, if you take plus 4 minus 6, you get minus 2, which is the charge on the carbonate ion. If we then take account of all the math here, plus 2 plus 4 is 6, minus 6 is overall neutral. So if I take plus 2 plus 4 minus 6, the overall charge on K2CO3 is neutral. If we separate the carbonate ion by itself, then we can take the plus 4 minus 6 equal to minus 2 for the charge on that ion. So in other words, the sum of all the oxidation numbers equals the charge on the molecule or compound or ion. So here we have an ion, so the oxidation numbers of carbon and the 3 oxygens sum up to minus 2. If we have the whole compound of K2CO3, which is overall neutral, then all 3 of those oxidation numbers for the atoms sum up to the charge of neutral. But of course, we have to account for 2 potassiums, 3 oxygens, just 1 carbon. Okay, the next slide has a bunch of examples that hopefully take us through kind of the range of rules and possibilities. Whenever we see an element just by itself, we just have like iron, H2, things like this, this just has to be neutral, meaning the atoms in those compounds haven't built up any charge. If you're picturing H2, like each hydrogen still kind of has that net 1 electron. That is another reason why each of these atoms would be neutral in charge. Neither one of them, if one of them were positive in H2, the other would have to be negative. That doesn't make much sense either. So neutral for the 2 hydrogens. Helium, noble gas, would of course be neutral. If it's not neutral, there'd be a charge indicated for the atom. Br2 liquid, that's also an element, so that would be 0. What about Al2O3? The only charge of aluminum is a plus 3. This should be an ordinary oxygen. So by rule, we should know plus 3 and minus 2. We can double check the math. Plus 6 for the 2 aluminums, minus 6 for the O's, overall charge neutral. So by rule, we can get Al and O just from their general rules, that aluminum's only a plus 3, oxygen's only a minus 2, and we can check the math and it works out. Calcium's only charge is a plus 2. So hopefully we're seeing that this kind of like reinforces some topics from nomenclature. Nitrogen, simple atomic ion of nitrogen, it should be a minus 3. Now let's say we didn't know that this is a minus 3. We could deduce it, right? Because we could say there's a plus 6 from the 3 plus 2s. And then you have to have a minus 6 for the overall 2 nitrogens. So minus 6 divided by 2 is minus 3 overall. Calcium sulfide, by rule, 2 plus, 2 minus. Sulfide's in the oxide group, or in the oxygen row, and so it should be a minus 2 ion. But we can double check or just use the deduction from knowing calcium, we can get sulfide for sure. Because if you recall, sulfide, there was no rule for sulfide, so we can either deduce its charge off of calcium's charge or just by inference by being in the oxygen group. Barium hydrides, like calcium hydride, barium's an alkaline, plus 2, so minus 1 for each of the H's. O2F2 is another compound of fluorine. There's not a lot of stable compounds between O and F, but this is another one of them. So we go minus 1 for the F, so this is what we know. And then what we deduce is that oxygens have to be plus 2. There's 2 of them. So oxygen's oxidation number would be plus 1. So all we're trying to learn is like what's the priority system, if you will, or what charges trump others, or where do we begin assigning charges. It was just with what you know the charges of by simple rule. So we know potassium's a plus 1. There's no other charge potassium can be in KO2. So we get a plus 1, minus 1 for the 2 collections of O's. So this is the superoxide. So that's where each O is minus a half. So minus a half times 2 is minus 1. And so then also by name, that would be potassium superoxide. And superoxides are the case where oxygen has an oxidation number minus a half. Calcium peroxide, we did this one earlier, but plus 2. And then minus 2 for the entire collection. So per O, think of oxidation numbers per atom, not per group. So the O2 group as a whole is a minus 2. So each one individually is minus 1. Now there's no rule for carbon, so you got to look to oxygen first, so -2 for oxygen. Now you could again think, is this a peroxide or superoxide? Just go back to what we said earlier, that we're not making peroxides and superoxides with carbon. We do make them with hydrogen, so you can have hydrogen peroxide. Maybe we'll look at that in a second. But carbon, this is just ordinary oxygen. So this is just ordinary O times 2 for -4. So carbon's a +4. Now let's look at that hydrogen peroxide case, because that's the only other element that will make a peroxide other than the alkali or some of the alkaline metals would be hydrogen. And then, of course, we would know the oxidation numbers here because we know hydrogen's rule is +1, so a +2. So here you get an overall -2 for the two O's. And so this is a simple formula for H2O2. There's that joke. I hate being the chemistry guy telling stupid jokes, but dad jokes or whatever. So a guy goes to a bar, orders an H2O, and the guy next to him says, I'll have an H2O2. And then he died because he got an H2O2. So don't drink hydrogen peroxide. Again, this goes back to, like, just because you know the formula and the name and all that stuff doesn't mean you can drink it or ingest it or it's safe to work with. So let's keep that as a mantra. You guys have heard that before, right? Yeah. Hopefully your dads have told you some dad jokes. So -4 for the two O's for MnO2, so +4. So by name, manganese 4 oxide. And so again, if you can think of the name, that can help you also figure out the oxidation number. So if you know the name's manganese 4 oxide, then you know the charge and oxidation number of manganese is +4. So to some extent, we still have to know, like, or if we remember formulas of molecular ions like ClO4, ClO4 is derived off of chlorate, which was ClO3, so this is perchlorate. The charge is -1. The charge of this one being -1 overall, that's where we kind of go first to get copper as a +2. And so we kind of have to still remember charges of ions. So that helps us determine, and that's how we're getting this +2. And then from there, we can break down ClO4 either combined in the formula for the whole molecule being neutral, or we could break it apart and just say, well, let's work out the charges for chlorate separately. For perchlorate separately. So each O would have to be -2 by rule. There's 4 O's, so -8. And then chlorine's charge has to be whatever makes 8 taken away from it equal -1. So that would be +7. So if chlorine's +7, subtract 8, you get overall -1. That's how we can get the charge on chlorine's +7. And oxygen's -2. Now, can you show this for the full formula too? So if we go to the full formula, that we should be able to take +2 for the copper, and then we have 2 chlorine, so it'd be +7 times 2, and then we have 8 oxygens times -2, and so that math there. So +2 plus 14 is 16, -16 is overall neutral for 0. You could also have said, well, if we didn't yet know the charge of chlorine, if we were just looking at this example here and kind of setting this math up here, we could have derived that that should be 7. That's the only number the charge of chlorine can be to make the overall charge of KClO42 equal 0. So a couple of different ways. You can break an ion down by itself if you know the charge of the ion, or you can just look to the overall formula and use the collection of 1 copper, 2 chlorines, 8 oxygens in total. What about ClF3? Again, it's just a matter of, is it chlorine or fluorine that's -1, and it's fluorine. So fluorine wants the negative charge. There's 3 of them, so that's a -3. So making the charge on chlorine +3. CCl4, here we can use that chlorine should be -1. So we just couldn't begin the previous problem with chlorine as -1 because it adjusts accordingly with fluorine. But with carbon, chlorine just goes ordinary -1, and then carbon adjusts accordingly to +4. So the way oxidation numbers work is if you're given a problem, you should probably, for all but one of the atoms, know by rule what the oxidation numbers have to be, and then you can infer one other element in the formula for something you don't know. So just to do one more example, if you have like K2SO3, so it's like by rule I know potassium, by rule I know oxygen, sulfur is the one that we can deduce. So we know +1, we know -2 for each O. So that helps us get sulfur as a +4. Okay, then where we put oxidation numbers into use is then predicting whether reactions involve this change of charge and fit the category of being an oxidation-reduction reaction. So losing electrons in reaction is oxidation, gaining electrons is reduction. I've also seen students tend to remember oil rig, where oxidation is losing electrons, reduction is gaining electrons. And so in this reaction here, by rule, we have oxygens and hydrogen at 0, +1, -2. So this is how we're seeing hydrogen losing an electron to go from 0 to -1. So H is losing electrons. So we're going from an H to an H+. So that's the loss of an electron. So the electron's given off by hydrogen, and then oxygen absorbs the electron. It doesn't fly out off and disappear. The electron has to be absorbed by something, and so our O atoms is what's gaining the electrons. So O is going from 0 to -2. So that's each oxygen atom absorbing 2 electrons. So if you notice, we have twice as many hydrogen atoms in the reaction as we do oxygen, so we can lose twice as many electrons off hydrogen and then have those electrons absorbed by half as many O atoms. So we have 4 H's losing an electron, so we have 4 electrons being lost in the reaction. And then we have 2 oxygen atoms gaining 2 electrons each. So we have 4 electrons being gained. So we're not creating or destroying electrons here, we're just changing where the electrons are on their respective atoms. And so this reaction is an example of what we call a redox reaction. So this is a redox reaction. What about the next reaction down? So here we have lead solid, so metallic lead or elemental lead as a neutral atom dissolving in nitric acid. So we have +1, -1 nitrate. And so here we're forming lead 2+, and then nitrate's still a minus, but then hydrogen's going from plus down to 0. So we're going the opposite direction here. H+ is going to H, and lead is going from lead to lead 2+. So just think for a minute, which atom is oxidized, which atom is reduced in this reaction here. So lead neutral is losing 2 electrons, so the lead atom is oxidized. And then it's the H atom that's undergoing the reduction. Reduction's gaining electrons. So H plus an electron goes to neutral hydrogen. So this is hydrogen being reduced. So if you can pick out in a reaction when an atom is being oxidized and another atom is being reduced, then you know that's an example of a redox reaction. So this is a redox reaction. So this is an oxidation reduction reaction here, because we have the charge being transferred from lead to the hydrogen. So you can see which atom's losing electrons, it's lead. The atom's gaining electrons is hydrogen. The nitrate staying NO3 minus on both sides of the reaction. It's actually the spectator ion as well. So nitrate's unchanged. So the nitrogen and the oxygen and nitrate are not part of this oxidation reduction. They're just staying the same. So the nitrate is unchanged. If we were to write, I don't think I'll go through the process, but if you imagine writing is HNO3 is a strong acid, strong electrolyte. If we were to write a net ionic equation, the nitrate would be disappearing. So we just have lead plus the 2H plus goes to Pb2 plus H2 as our net ionic equation. So then one last thing to kind of check or to think about is to go back to like a metathesis reaction. So metathesis reactions generally are not going to fit the category of being redox reactions. Well, why is that? Well, just try to address the question, is there any charge being transferred? And so here we have silver plus, nitrate minus, K plus Cl minus, and here we're forming silver plus, silver minus, or Ag plus Cl minus, and then K plus NO3 minus. We are doing a reaction. We are doing a metathesis reaction. We're exchanging ions, but we're not changing the charge of the ions. So there's no change in charge. No atoms are oxidized or reduced. So no atoms are oxidized or reduced in a reaction, then it can't fit the category of being one of these redox reactions. So I just want us to see that not every reaction that we've looked at would be an example of a redox reaction. So redox reactions just involve the exchange of charge. We can see that from assigning oxidation numbers in the reactants and products, and then trying to see from the reactants into the products what was the change that took place for those atoms. So we can pick out which atoms gained electrons and were reduced, and which atoms lost electrons and were oxidized. I think with this topic, there's some topics where you got to remember a mnemonic. Forgetting which one's oxidation and reduction is very common, so just have some way to remember that the loss of electrons is oxidation, the gaining of those electrons during the course of a reaction is reduction. Now this chart here shows for some of the elements in the periodic table, it shows the relative ease of oxidation, where the ease of oxidation is highest at the top of the chart. And if you notice at the top of the chart, we have things like alkali metals, we see some alkaline metals, we see sodium, magnesium, then aluminum. So we're seeing some of the more commonly found metals in ionic compounds at the top of the ease of oxidation chart. And at the bottom of the chart, you're going to see more examples of metals that you probably more frequently encountered in their metallic form. So things like copper, silver, mercury, platinum, gold. We often call these metals down here coining metals because they're so stable from oxidation that you don't have to worry too much about them being oxidized in ordinary conditions. If they get wet, for example, that they're not going to necessarily oxidize very easily. So these are more precious metals towards the bottom of the chart. So they have a less likeliness of being oxidized. So you're going to be more likely to find these metals still in their metallic form. You're going to be more likely to find these elements towards the top of the chart in their cation form. Though you could possibly have seen, you've certainly probably seen or worked with copper solutions, and as well, I doubt you've seen like sodium, but you can buy sodium metal where you can do some chemistry or work with like sodium metal. It's just going to be that sodium metal will be much more reactive and more dangerous to work with and to handle than say copper metal is. Copper metal, we see it in pipes, and it's stable enough for water to flow through it. Now, one of the things that's interesting is that hydrogen's kind of in the middle and like lead's on top. And like, it's interesting here that lead, and we already saw in the previous example, lead dissolves in acidic solution. And so that's where lead piping is so bad, is because lead can leach into water if the water's corrosive. So you have water with relatively low pH, relative high acidity, then lead can start leaching out into the water. So you can kind of see from this chart here, if you were designing a plumbing system and you were choosing between lead and copper, you'd probably choose copper. Because copper is going to be less reactive with corrosive solutions. Now, I mentioned this chart here. So there are a set of questions where we can use this chart to predict when redox reactions occur versus when they don't occur. You might see some problems like, does copper dissolve in zinc sulfate, or will zinc dissolve in copper sulfate? And so copper is more stable, doesn't dissolve in zinc sulfate, but you can take the zinc because it's more reactive, it's higher up on this chart. Zinc would dissolve in that copper solution. And then the copper solution would go back to copper, the zinc would go to zinc 2+. Makes a lot of sense. But we're not going to test you on these concepts. We're not going to test you on the knowledge and the use of what we call the activity series to predict when redox reactions occur. You could also predict when things dissolve in acid You might see some questions. I try to tag them on the daily quizzes for the ones that are from these topics so you know not to worry about focusing on those problems for the exam. So we're not going to test you this spring as well on the use of this activity series and solving problems with it. I think it's useful to know, it's useful to kind of imagine that elements have a range of ease of oxidations, and it goes with exactly as you would predict that alkalis, alkaline, aluminum are on the high end, and then the precious Corning metals are on the low end. Okay, so with that, we'll move into the next section. So there's two more sections that kind of go in chapter 4, and these start to get into some of the quantitative aspects of solutions. So where we can start to understand concentration units like molarity we'll discuss here. And then with molarity, we'll see that we can start solving problems related to stoichiometry in the very last section. So the last section we'll get into what we call solution stoichiometry problems, where we can solve problems that look like chapter 3 problems, but with the solution unit of molarity being involved. So what molarity is the moles of a solute dissolved in a liter of solution. And so molarity is the moles of whatever your solute is dissolved in the volume of solution where that solution's in liters. And we have some units here where 1 molar, so 1 capital M, is equal to 1 mole of a solute per 1 liter of solution. So SOLN is my abbreviation for solution. So you have the volume of the entire solution versus the moles of just the solute particle. So we could prepare a solution by taking some mass of calcium nitrate. You can take calcium nitrate powder, it's relatively pure, weigh it out on a balance, add and dissolve it into water, and you can dissolve it into a total solution where the total solution volume would be about 1 liter. If you had 1 liter of this solution, then you'd have 1.25 moles of the calcium nitrate dissolved in that liter of solution. So what this would mean here is you have 1.25 moles of calcium nitrate per liter of solution. So we'll use this capital M unit a lot, and one of the things that I usually say is whenever you see the M, just think that it's mole per liter. So it's the moles of that thing per liter of the entire solution. Now, the reason why this is the liters of solution and not just water, so whenever you make a solution, like if we just took 125 milliliters of water and mix like 1.25 moles of a compound into it, the compound usually pulls the water in more closely and usually decreases the volume of the solvent that you started with. So a lot of times what we would do is you would just put 1.25 moles into a flask, like a volumetric flask, terrible at art, but picture here where you have a line on a flask where you have like a 1.00 liter mark. So the way you would do this is you would try to put 1.25 moles of a compound into the container, so it's solid in the bottom, and then start filling with water, dissolving the compound until you reach precisely that 1.00 liter mark, so that you know the volume of the solution. You may have added slightly more than 1 liter of water to make the solution, maybe a little less depending on the solution properties, but it doesn't matter because you're just trying to say what is the total volume of the entire solution where that compound dissolved into that water. And so then what we might then do is say, well, you could take 25 milliliters of this solution and then deliver a certain quantity of that solute in that volume. So let's say you had 25.0 milliliters of the solution, so mLs. You could ask, like, how many moles is that? So how many moles of solute of the calcium nitrate are present in 25 milliliters of this 1.25 molar solution? So the capital M will usually pronounce that in vocabulary. Molar would mean moles per liter. So the way this could work is we could just very easily take this as 0.0250 liters, convert it to liters. So our number of moles would equal 0.0250 liters. and then it's 1.25 moles of that solute per liter of that solution. So that's why the molarity unit we use moles of solution is so that you can take 25 mils of a solution and then know that the number of moles there would just be 0.025 times 1.25. So that's 0.0313. So in other words, all you got to do is take a volume times the molarity. The volume in liters times the molarity moles per liter gives you moles. So sometimes we might write it like this, that molarity, capital M, is moles over volume. And so N is usually the symbol for moles, and V here is solution, the volume of the solution. So molarity is moles over volume. All right, so there's another question on this packet here. So we can then also come back to the idea that the solution really isn't calcium nitrate, right? It's really calcium ions and nitrate ions. And so you could say, well, the concentration, when I write brackets, it would be the concentration of what's inside. The concentration of calcium nitrate is 1.25 molar, to which you might say, well, technically it's 0 molar, but let's not get that, think that level per se. Because like calcium nitrate's not stuck together. The actual concentration, this solution is really calcium ion, Ca2 plus, and so the brackets always mean the molarity of what's inside. So when we see the bracket, this is going to mean what's the molarity of what's inside the bracket. So the molarity of the calcium ion, how many calcium ions are there per liter of solution? Well, for every mole of calcium nitrate, there's just 1 mole of calcium, so this would also be 1.25 moles per liter. So that's 1.25 molar calcium ion. And then, of course, the other ions, nitrate. So the concentration of nitrate ion, so the molarity of the nitrate ion, is that we're getting 2 moles of nitrate for every 1 mole of calcium nitrate. So I'm getting 2 of these nitrate ions, so this is going to be 2.50 moles of the nitrate ion per liter of solution. And that's just because there's 2 nitrate ions per 1 calcium nitrate. Pretty obvious, right? And so then one last thing we might write, and sometimes this is a little confusing, but hopefully once we see this, or if we just put the thought into it, what would the total ion concentration be? What would be the total concentration of the calcium and the nitrate ions? Well, we could just add these up. So that would be 3.75 moles of total ions per liter of solution. So this kind of goes back to electrolytic behavior. So if you think of electrolytic behavior, the more ions, the more electrolytic. So if I had a 1.25 molar KCl solution, so let's say we're comparing this with 1.25 molar KCl, where you have K plus Cl minus, well, this would just be 2.50 molar ions. So even though you have the same molarity of solution, even though you can have a 1.25 molar KCl solution, a 1.25 molar calcium nitrate solution, the calcium nitrate solution would be more electrolytic. So the electrolytic behavior, the more ions we have, the more electrolytic. The fewer ions we have, the less electrolytic. Think of that to mean if we were trying to light up a light bulb like we did in that demo, the more ions, the brighter the light bulb. The less ions, the less bright the light bulb. And so this might be then the case where you compare, like imagine you have a mole of this, a mole of that, a mole of, like, so imagine this example here. Let's say you 1 mole of each of these into water. So let's say we're putting, A, we're putting, KCl. B, we're putting K2 CO3, another water-soluble ionic compound. Let's say C, we're putting H2CO3, a weak acid. And let's say for D, we're putting methanol. Can we rank these in order of the electrolytic nature of the solution? So like, which solution is most electrolytic? Which solution has the most ions in it? We put 1 mole of either KCl, 1 mole of K2CO3, 1 mole of H2CO3 versus 1 mole of methanol into a liter of water. So the compound here that makes the most ions is B, because we're getting 2 moles of ions per mole of compound, right? So that's going to have the greatest electrolytic nature. It's going to light the light bulb up the brightest, if you think of it that way. Then A is going to come next, because we're at least getting still, 2 ions into solution. Previously, though, with K2CO3, we're just getting 3 moles of ions into solution. So we're getting 3 moles of ions for B into solution. We're getting 2 moles of ions for A into solution. But for C, we're only getting some. This is a weak acid. So we're getting like less than 3 moles of ions. We're probably getting very few ions into solution here because it's a weak acid. We're getting just a small bit of H plus and HCO3 minus into solution. Just a small amount of those ions. In some ways, this is a bad choice. Let me actually make this a slightly different choice real quick, and I'll explain why. Let me make this H2SO3 real quick, just because carbonates are weird. Like, that thing's really not going to give you any ions in solution for the reason we were talking about earlier on those acid-base reactions. H2CO3 just decomposes to water and CO2. So let's get rid of that problem. Let's have H2SO3, which is an acid you can put into water and doesn't decompose into some other molecules. This thing here would break apart into the ions as you would expect by it being a weak acid. So like, being a weak acid means that you get partial dissociation into H plus and HSO3 minus ions. So you're getting nowhere near 2 ions per mole of compound into the solution. But you're still getting more ions than you get for D, because D doesn't give you any ions, because D is a non-electrolyte, doesn't ionize at all. So for the non-electrolyte, methanol and water is not going to light the light bulb up at all. If we have a 1 molar solution of H2SO3, it'll probably make the light bulb very visibly bright, so it'll probably give the light bulb a little bit of light, and then more light for A and the most light for B. So you can rank by the electrolytic nature, or just really start to think about how these solutions vary in terms of their number of ions, and start to quantify or think how we can quantify those concentrations of ions. Now, we can also then take a concentration of a solution and change it by adding water and diluting the solution. So this slide here is showing how we can do a dilution, where we're taking 25 milliliters of some stock 1 molar solution of whatever the compound is, probably copper. Copper solutions are usually blue. So let's say you had 1.00 molar, say, copper nitrate. And so 1 mole of this compound per liter solution, you take 25 mils of it, add it to a new flask, and then you fill that new flask to the 250 milliliter mark with more water, as much water as it takes to fill to that mark. So our new solution volume is 250 milliliters. What we've done is we decreased the concentration of the solution by a factor of 10, because we've taken 25 mils, diluted it to 250. The new concentration becomes 0.100 molar. So how do we know that that's the concentration? Well, one way would be to think, well, the number of moles here would be the 0.025 liters. So just the volume in 25 milliliters in liters times 1 liter, so 0.025 moles is our solute. And we're just dividing by our new volume of 0.250 liters. So we go mole solute per liter of solution. So this is our new solution volume. We started from 25 mils. We presumably added about 225 mils of water, somewhere in that ballpark, to get to this total volume. So 0.025 divided by 0.25 is 0.1 molar So we've gone from 1.0 molar to 0.1 molar by diluting that solution. And so we can derive an expression or use an expression that looks like this, where we can take an MIVI and equal an MFVF, meaning we can take an initial molarity, initial volume, and then equal to the final molarity times the final volume multiplied together. This is a dilution equation. So this equation here, we can use this whenever we're doing dilution. And the reason this works is if you think of M times V, that gives you moles. So this gives you your initial number of moles. And then we're not changing the number of moles when we do a dilution. The moles of the solutes would stay the same. We're just taking a certain solute and diluting it with more water. So the moles before and after are the same, which makes the final molarity times the final volume equal to the initial volume times the initial molarity. So this is a common equation that we use. Pretty easy to see where it comes from, but then it applies to dilution problems. So we'll start class next time with a problem using a dilution equation or dilution step, and then we'll get into some stoichiometry problems and wrap up chapter 4. All right, guys, that's it for today. Have a great day.